Today's topic is Converse of Urysohn's lemma. In the last lecture, we have proved Urysohn's lemma that it states that if a space is normal, then for every pair of disjoint closed sets, there exists a continuous map which separates them. And the converse is if in a topological space for every pair of disjoint closed sets there exists a continuous map which separates them, then space is normal. Now the theorem states that if for any pair of disjoint closed sets A, B in a topological space X and there exists a continuous function f from x to close interval 0, 1 such that f of x is equal to 0 for every x in A and f of x is equal to 1 for every x in B, then X is a normal space. Let us prove this theorem as left close and right open interval 0, half and left open right close interval half 1 are open in closed interval 0, 1 with respect to the subspace usual topology. Why? Because if we take open interval minus half and half, then this is clearly open in the usual topology. And if we take its intersection with closed interval 0, 1, then we get the first interval. And so the first interval is open in the closed interval 0, 1. And similarly, if we take uh, an open interval half and 1.5, then this is open in the usual topology. And if we take its intersection with closed interval 0, 1, then we get the second interval. And so the second interval is also open in the closed interval 0, 1. And since these intervals are open in closed interval 0, 1 and since f is continuous, so inverse images of these two sets are open in X, as we know that inverse image of any open set under a continuous map is open. Let us denote these inverse images by L and M respectively. Then L and M are open in X. We will show that L and M are disjoint open sets in X such that A is contained in L and B is contained in M, because we have to show that space is normal. As it is given that f of x is equal to 0 for every x in A. So if we take inverse image of singleton 0 under F, then that will contain A. And since f of x is equal to 1 for every x in B, so if we take inverse image of singleton 1 under F, then that will contain B. Also, inverse image of singleton 0 under F is contained in inverse image of left close and right open interval 0, half under F, and that is equal to L. And since F inverse of 0 contains A, so here we find that A is contained in L. And inverse image of singleton 1 under F is contained in inverse image of left open and right close interval half 1 under F, that is equal to M. But as we have seen earlier that B is contained in F inverse of singleton 1, so B is contained in M. So A is contained in L and B is contained in M. Now we want to show that L and M are disjoint. So L intersection M is equal to F inverse of left close and right open interval 0, half intersection F inverse of left open and right close half 1 interval, and that is equal to F inverse of intersection of these intervals. But as these intervals are disjoint, So here we get L intersection M is equal to F inverse of phi, and this is equal to phi. So we have shown that for two disjoint closed sets A and B, there are two disjoint open sets L and M such that A is contained in L and B is contained in M. Hence, X is normal. Now we have the following theorem, which states that a topological space X is normal if and only if for every pair of disjoint closed subsets A, B of X, there exists a continuous function f from x to close interval 0, 1 such that f of x is equal to 0 for every x in A and f of x is equal to 1 for every x in B. Now, this theorem can be proved by using Urysohn's lemma and its converse. Thank you.